All right, guys, in this video, we're going to be talking about describing distribution or position in a distribution. So that's going to be like this whole idea of like z-scores and using that like normal CDF and like that normal PDF when we're like looking at different types of data distribution. So this first question here says, suppose the mean of a data set is 55.8 and standard deviation is 12.2. So let's get that written down. So here's x bar is 55.8, and then we have SX, or standard deviation, is 12.2. What would the new mean and standard deviation be if you added 10 to each data point? So if you think about your data, if you're adding 10 to everything, then your mean is just going to increase by 10. So my new mean is going to now be 65.8. But my standard deviation, when I look at like how much things are deviating, when everything's being added 12.2, or when everything's getting added 10, it's still going to say 12.2 apart. So when you think about that, like let's think about like real world scenarios for a second, right? So like let's say that you have like 4 tests, and let's say you had a 65, a 75, a 70, and then an 85. The deviation is like how much on average does that vary from the mean? If I added 10 to every single one of these now would be 75, 85, 80, and 95. The variance between is still going to be the same. However, the average is going to be exactly that much higher. What would the new mean and standard deviation be if you multiplied each point by 5? So multiplication is a little bit different. When you multiply, both the mean and the standard deviation apply. Because if you think about this spread of data, if I'm looking about this, like let's think about this as like a box plot. If I have my data set and I add 10, all it does is it shifts my box plot to be 10. But if I think about my box plot and then I'm multiplying by 5, what that does is it spreads everything out in a different way. So what this does is it means that not only does my mean multiply by 5, but my standard deviation multiplies by 5. When I'm looking at these next questions, we're looking like normally distribution. So remember, with normal distribution, we're thinking of that normal curve. And remember, each standard deviation has a different value. So here's where your empirical rule comes into play, where like it's like 68% of the data is within 1. And then within 2 standard deviations, that's 95%. And then within 3 standard deviations, that's that 99.7%. So when you look at like what percent of the light bulbs can last within 1 standard deviation of the mean, 1 standard deviation of the mean is going to be 68%, because that's 1 standard deviation above and below. That's 68% of that area underneath that curve, where like that whole entire curve equals an area of 100%. A company considers a light bulb defective. It can only last 50 hours straight. What portion of the light bulbs would this company consider defective? So I'm going to grab my calculator out, and we're going to go over to this like second vars, because that's going to take you to that distribution. We are going to go into this second vars. Remember, we're looking at that normal, we went normal CDF. I did that twice. I'm obviously tired. This is why you don't make videos at 10 o'clock at night. And you're going to be putting in those upper and lower boundaries. Because I'm looking for only 50 hours, so I'm looking for less than or equal to 50 hours. We're saying like 50 hours, what proportion would consider defective? So that's 50 hours or below. Remember, you want a lower value of a really small number. I'm just going to leave this. You could also say like negative, like I don't know what that is, like 1 million or something. And then we can come in here and say that our mean is 62. And then our standard deviation is 4.4. After you click that paste, it should give you an idea of like that value under the curve should be 1 to about 0.31%. So very small. And let's actually round that up to 0.32. So 0.32% or 0.0032. Both of those are acceptable answers. Remember that when you're asking for portions or proportions, it needs to be a value less than 1. An energy efficient bulb can stay lit for at least 68 hours. What percent of incandescent bulbs can stay lit for that long? So really what we're saying is like greater than or equal to 68%. Or 68 hours. Sorry. And we're looking for like what percent of those last. So the same thing, we're going to go to that second vars for that distribution, normal CDF. Since we're looking for greater than or equal to 68 hours, my lower bound is going to be 68, and my upper bound is going to be a really big number. Remember, the reason we do that is because when we look at these curves kind of like have this horizontal asymptote. So that means they're never going to exactly like touch that y-axis. So we can't like negate the fact that there's like low key some values that are going to exist way far to the right. So same thing, my mean is 62, my median is 4.4. So I'm saying everything from 68 all the way up to a really large number is going to gather most of my data. And when I press paste, if I take that, it's going to be either, it asks for percent. So let's move that decimal place 2 times or like multiply by 100, right? So I get that that's going to be about 8.634%. And 3 decimal places is always kind of like the golden rule if you're going to be rounding. What portion of the light bulbs can stay lit for between? So remember when we're looking for between, that's actually really nice because we don't have to estimate those upper and lower bounds. So that same menu, second vars for that distribution, except that lower is 55 and that upper is 65. And when I do that, it asks for what portion. So remember, you can leave it as a decimal or you can write it as a percent. So 0.697 or 69.7%. This one is working backwards, so the top 2%. So how I kind of remember this whole idea is if I go to that distribution bar, we're like reversing what we already have. So I'm going to that inverse normal, and I'm saying, okay, if my area, the top 2%, that area is going to be that 0.98. So we're saying like what of that value makes up like that 98th percentile, right? My mean, same thing as 62. The top 2% is that 98th percentile, right? And then my standard deviation is 4.4. Don't worry about the tail. That comes into play way later. And you're just going to go in here and paste these values in. And that should be about 70.420 hours. And all we did is we said that at that top 2%, right here, this value right here would be about 70 hours. So for this next one right here, when we're talking about comparing distributions, it looks like Sophia did better on her statistics test, but remember, we're always talking relative. We did this when we talked about like who was the greatest of all time basketball player, right? Like Michael Jordan versus Wilt Chamberlain, and we said that it's all relative to their surrounding statistics or like how the game was played at the time. So very similar, even though you have a higher grade in one class, that doesn't mean that you're like necessarily like doing better in comparison. So for this guy right here, I did both of these like normal CDFs. So I went to that second vars, normal CDF. I just like left that lower boundary normal and I said if we went from some really tiny number all the way up to 95, her grade on her calc test, where the average on her calc test, well, statistics test, sorry, her average was an 87. of the class and the standard deviation was a 7, we can say like, okay, where would she be? Like what percentile? And she's in the 87th percentile. But if we pulled all these numbers for calculus, she was actually in the 93rd percentile for calculus. So she did comparatively better on her calculus test. You also could have found the z-score. And remember that z-score is found by saying like what was the score minus the mean divided by the standard deviation. So you could have said like how many deviations is it away from the mean. So let's actually get that calculated for both of these. So for both of these guys, let's say, and like we can use some subscript here, right? Like let's say like z stats and let's say like z calc. So we're going to say her score was a 95 on stats and a 91. Sophia's kicking butt. On calc, the average of the statistics test was an 87. For calc, it was an 85. 87. And then my standard deviation was a 7 here, and my standard deviation was a 4 here. So we can get those values pulled up really quickly. So we can say, all right, we had 95 minus 87 and divided by 7. So my z-score here, we're 1.14 standard deviations away from the mean, or like to the right of the mean. Let's give it 3 decimals just for that golden rule. And for this next one, you have that 91 minus 85. And then we're dividing that by 4. So we have 1.5. Because this guy is 1.5 standard deviations above, right? If we think about our normal distribution, 1 standard deviation above puts us like at this percentile, but if the further we go, right, the higher percentile we're at. So we really see that she did better in calculus. I'm going to let you guys look at the key for the rest of these. But that was how you would work your calculator for z-scores, also for percentiles or working backwards from them.